Hello, Dr. Winkler, and welcome to Computer Science Chats. How are you?
Very good, thank you.
So I've prepared several questions to ask you. First, could you please introduce yourself and your educational background?
Okay. My name, as you said, is Peter Winkler. I was born in California, uh, raised in large part in New Jersey. Um, I went to Harvard as an undergrad, um, then went to work for the government, then joined the Navy. When I got out, went to graduate school in mathematics, wrote a PhD thesis in logic, and um, took a postdoc at Stanford and then a regular academic position at Emory University in Atlanta. Um, at that time, computer science was largely in its infancy. I regarded myself as a mathematician, interested in logic and later discrete mathematics, combinatorics. Um, didn't really I was really introduced to computer science by a student, an undergraduate student at Emory, a guy named Sam Buss, who went to a meeting called Fox Foundations of Computer Science and came back to Emory with this big proceedings of the conference and told me about all this exciting stuff going on there. That's when I became aware of this whole community for the theory of computing. I was at Emory for 12 years, and then I went to work for Bell Labs. And I had become chairman and eventually professor at Emory, but I got interested in a problem involving the addressing of the internet, which had come up at Bell Labs. And I won some money for solving that problem and ended up going to Bellcore and then Bell Labs, working for them for 15 years. That was great. And then eventually I got back to academia in 2004 to Dartmouth, and I've been there ever since. At Dartmouth, I belong to both the math department and the computer science department.
Thank you. So I know you mentioned that your career originally started in mathematics. So what was it that inspired you to first pursue mathematics?
I guess when I was a kid, I was good at math. You tend to like what you're good at. And I always thought math was a lot of fun. I especially enjoyed doing mathematical puzzles, and now I write books on mathematical puzzles, in addition to the research I do in mathematics and the theory of computing. Yeah, math is fun. It's everywhere. Computers make it even more fun. I like it. Yeah, that's basically your answer here.
Yeah, thank you. So I know you're a professor of mathematics and computer science. So how would you describe computer science or computing fields and their connection to mathematics? Like, how are they related?
Yeah, it's a good, complex question. They're very strongly related. Almost every part of computer science uses some kinds of mathematics or other. And and these days, computer science, it creeps into many parts of mathematics as well. Many mathematicians have become interested in using computers for experimentation, sometimes using computers to actually prove things, using computers for motivation. So the two fields are, in fact, very close. Interestingly, at Emory, where I used to be, and at Dartmouth, where I am now, the computer science and mathematics were the same department for a very long time. Emory only very recently split. I mean, people regard the two subjects as being different subjects, and each one very worthy on its own, for sure. But there's lots of computer science and math, and lots of math and computer science. So some of the fields of computer science that use math very heavily, graphics, security, because cryptography is all about mathematics. Robotics uses mathematics for motion planning and all kinds of other stuff. Systems uses the mathematics of engineering. Machine learning is heavily into mathematics, as you might expect. And my favorite area of computer science, which is the theory of computing, really is mathematics. I mean, if you do the theory of computing, then whether you like it or not, you are a computer scientist and you are a mathematician. So in that field, the two areas definitely overlap. And lots of my colleagues belong to math departments. Lots of them belong to computer sciences. Some of them, like me, belong to both. So yes, the two areas are very heavily intertwined.
Yeah. Could you describe some of the activities that you do through your work?
Hang on a little bit. I'm going to increase your volume a little bit so I can hear you better. You asked me to describe some of the activities.
Activities.
Yeah. Well, of course, first thing you think of is research. I do research in the theory of computing, which, as I say, is mathematics as well as computer science. There, the basic question is, what kinds of things can a computer do? What kinds of problems can a computer solve? And here it's usually a question of efficiency. Victor, you may have heard of something called combinatorial explosion. If you try to solve a problem by checking every possible answer, like if you try to solve the traveling salesman problem by considering every ways in which the cities where you visit can be ordered, there's too many. Even the fastest computer we can possibly imagine won't be able to solve this problem in less than 1 billion years or something like that. But there are many other problems for which efficient algorithms exist. We could solve them in sometimes a matter of nanoseconds. What's the difference between the problems that are so easy to solve and the problems that seem to be so hard to solve? We don't really know. We would love to know the answer to that question, and that's what the theory of computing is basically all about. It's supported very heavily by discrete mathematics. This is discrete spelled D-I-S-C-R-E-T-E, meaning mathematics of separate individual objects rather than continuous mathematics. And although continuous mathematics also enters into it. And also by probability theory, and sometimes algebra, and sometimes number theory, and all kinds of stuff. So the math that I do often involves discrete mathematics, combinatorics, graph theory, probability theory, and sometimes statistical physics, which also is increasingly tied to questions about the theory of computing. That's what kind of research I do, and yeah, other activities I mentioned. I like to collect puzzles and sometimes compose puzzles and write books about them. And I like to ride my e-bike, and I like to play squash, and I like to play bridge, and I like to make and listen to music and read books, and all kinds of stuff that you like to do probably too.
Yeah. So what do you like most and what do you find most challenging about these activities?
Well, the most challenging thing about research is that it's not so easy to. I mean, there's a lot of smart people working in math and computer science and trying to find, trying to do stuff that people haven't done before and trying to crack problems that people have been trying to crack for years and haven't been able to do it. It's not easy. It's not a good research, probably of any kind, is not a good thing to do if you get discouraged easily. In most jobs that you have, like you're a teacher or you're a salesman or you're a librarian or something like that, you get up in the morning and you're going to accomplish something, right? You're going to do some people some good. You're a doctor, maybe you cure people. But if you're in research, most of the time you're stuck, right? You can go for a long period of time without accomplishing anything. So you have to will yourself to have the confidence to believe that at some point you'll get a little idea and eventually you make a little progress here or something good happens. But then it is exciting when that happens.
So I know that you were a math research director at Bell Labs and Lucent Technologies for a while. What was that like, and how did the experience in industry change how you viewed academia?
Yeah, so it was really fun. My group is called Fundamental Mathematics Research at Bell Labs. And Bell Labs was when I started, it was part of AT&T. Later, it became part of Lucent Technologies, and then Lucent Alcatel, and now it belongs to Nokia. But whatever it is, it was part of a global network. And people would call or email from all over the world with their mathematical problems. So they would come to me as sort of the math doctor. And then I would farm them out to people in my group who included all different kinds of mathematicians. And these would sometimes lead to new theorems in mathematics, as well as to solving practical problems. So it was quite exciting. It was great to be inspired by real problems that come up in the real world. One thing that you do learn is that you almost never get a problem exactly right the first time you hear it. I mean, ideally in your mind, maybe somebody calls, this is a problem, it's completely clean, you know exactly what's needed, and you solve it and send it back. Doesn't usually work that way. It's a back and forth thing. It says, well, what we really needed was this. And as a matter of fact, well, that solution is great, but it wouldn't work for us because we need something that has also this property. So it's always a back and forth thing. And but still, sometimes when you finally learn what the problem really is from a mathematical point of view, it's the most interesting that it's been in all these iterations. So and it's great to get out there and do things in the real world. But it's also fun in academia where you can really you develop some tools and you can choose the problem that your tools are best for. So there are advantages to both, and I've had the benefit of enjoying both, and yeah, both. You could think of it as pure mathematics and applied mathematics. They definitely both have their joys, and they both have their challenges.
So you mentioned that you're also very interested in mathematical puzzles, and I know you've published a few books on that, like Mathematical Mind Benders as an example.
Mm-hmm.
How can mathematical puzzles, such as those in these books, be used to get a better understanding of computing?
Well, part of the answer is it depends on the puzzle. I mean, some puzzles really do, the best kinds of puzzles make you open your mind to a new idea, make you find it yourself. And that's so much more effective than just being told by some teacher or some mentor what the solution to a problem is that you're led to find it yourself, and then you really understand it. You can really use it when it comes up. So I think puzzles can be really inspiring in that way. They they get you to open your own eyes to something that you didn't really see before. But they also have this general nice property that they're fun and they get people interested. Um, I don't know if you've ever been in any of these Olympiad type competitions, Victor, but they're fun. You know, you um, you go and you meet a lot of other nerdy kids and who love to work on problems and puzzles and um, yeah, and I think the puzzle world has opened up quite a lot. I remember when I was a kid, it was mostly boys, and even just a certain kind of boys who were interested in puzzles. That's changed a lot. It turns out that girls like puzzles too, and people from all kinds of backgrounds. Um, and yeah, so yeah, I spent a year, as you know, working for the Museum of Mathematics in New York City, um, and it was lots of fun. And people come into the museum, and you can run classes for kids and for students and for executives, and um, everybody enjoys these things, and it gets their mathematical and computer science juices flowing, right? You often have puzzles of the form, find an algorithm to do that. I mean, that's a classic computer science problem. How do you do this kind of a problem in general? And other puzzles actually give you an algorithm and they ask you whether it works. And um, sometimes the question is, does this algorithm always work, or does it only sometimes work, or does it never work? Um, so yeah, well-chosen puzzles can really get you going. But I have to give you a caveat. I have to say that not everybody who's good at math or computer science likes puzzles. Um, some some of the world's finest mathematicians, computer scientists, they like to build theories and think deeply into problems, and puzzles for them might just be a distraction or something like that. So there's a matter of taste here. I love them, but um, some of my colleagues, when I say great computer scientists and mathematicians, don't bother me with puzzles. So take your pick.
I've also read that you have several patents. Could you describe what the process of getting a patent is like and talk a bit about how patents and more generally intellectual property issues impact work in computing?
Yeah, a little bit. My own background is as follows. So I always thought patents sounded like a fun thing to do. And one day I got an idea for a device which I called the electronic trusted party. Okay, a device that you could trust with information. So, for example, maybe you and I have each been trusted with a secret in the same. For example, each of us knows, has been told uh, who the next president of our university is going to be, or something like that. So we would like to find out if we both have the same information. Indeed, if we both have this information at all. I mean, I know I have it. How can I be sure you have it? But if I just tell you the answer, then I've spread the information, which I'm not allowed to do. But you can imagine you just have a little electronic device. It looks like a handheld calculator. I type in the name, I hand it over. It disappears. I hand it over to you. You type in the name, and the device merely says whether the names match. Right? And if they do, we can then talk openly about the person. And if they don't, we learn not to trust each other. Or maybe we learn not to trust our sources. Um, so I thought that, gee, this would be fun. Let me just try to see if I could patent this myself. Um, So I bought a paperback book called Patent It Yourself by some guy named, is it Alan Pressman, something like that. Book is probably still available. It's great. I loved it. Um, the book was a large format paperback with tear out forms, right? So you could just rip out these forms and fill them out and send them into the patent office. And it also had the book was full of cartoons of silly patents and stuff like that, and full of encouragement. And it turns out that it's really not hard to do that. If you this book or probably other books like it, um, they're fun to read. And it turns out not only is it quite doable to patent something yourself, but it's quite inexpensive to do so. There's a completely different set of fees if you have a lawyer do it than if you do it yourself. If you do it yourself, it's like 50 or $100. If you do it with a lawyer, we're talking about $1,000. I mean, it makes a difference. So I did that, patented something myself, and that had me learn the process. But now I have, I don't know, a dozen, 14 patents or something like that. And the rest of them are all done through organizations, either through Bell Labs, for example, or through my university, or with a group in a company that I'm doing consulting work for, or something like that. So I've never had to actually go through the process of sending in the forms and defending the patent myself. But it was fun to do that, and I highly recommend it. I'll give you an example of what can happen. Right? So I sent in my patent for the third electronic trusted party, and I got a reply. This is a back and forth thing. And the examiner said, I read your patent, but it seems to me that your electronic trusted party is like a hand calculator, except in some respects it's less capable. Okay? Because you put in something and you can't get the answer back out. And I wrote back to him and said, you're absolutely correct. This device is in some respects just a less capable hand calculator. But I said, that's a very important feature. For example, take a coffee cup, right? A coffee cup is capable of holding coffee in it, and it's also capable of spilling coffee, right? Suppose I invent a coffee cup which can't spill, right? Then you could say that this is a less capable coffee cup, yet it's clearly something that's useful and could be patented. Well, here I have a calculator that can't spill the beans. So he wrote back and said, good argument, and I got the patent.
Thank you. That's a really interesting story.
Right.
What advice would you have for high school students who would like to get into the intersection of mathematics and computing?
Oh, well, number one piece of advice, of course, is take courses in math. And if your high school offers a course in computing, and I think many of them do now. When I was in high school, computer science didn't exist. But yeah, sure. Sign up for courses. That's the first obvious thing to do. And I don't think any of your correspondents would have any trouble thinking of it. But there are also fun things you can do. One of them we mentioned, which is join competitions if you like that sort of thing. Another is to read puzzle books if you like that sort of thing. And in addition to puzzle books, there are other books on the market, popular books which are fun to read about computing and about math. there was a famous book when I was a kid called Mathematics for the Million, singular, by Lancelot Hogben, I believe was the name of the writer. And there was also someone around when I was a kid called Martin Gardner. Do you know that name, Victor? Martin Gardner was a theologist who loved recreational mathematics. And he persuaded Scientific American magazine to run a column called Mathematical Games, which he wrote for 25, 30 years or something like that. And he got millions of people around the world interested in the stuff. And he himself was only an amateur mathematician. His real expertise was religion, but he loved math. And he had lots of mathematical friends who would help solve problems and send in new problems, which he would publish. And Martin Gardner's books are widely available. Some of them are books of puzzles, others are books about strange objects called hexaflexagons, or about paradoxes, or even frauds that he liked to debunk. Reading the books of Martin Gardner would be a great start to just getting interested and having fun with math and in the early times of computers. So what else can you do as a high school student? Well, of course, you can play with your own computer. And that's actually fun to do. Just put in numbers and try things out, and you make discoveries that way. It's just amazing. Many people have special interests within math or computing. For example, you might be especially interested in numbers and number theory, or you might be especially interested in geometry. Maybe you're interested in tiling. Maybe you're interested in logic. I don't know. What do you like, Victor?
Yeah, I like tilings and logic.
Oh, yeah. I mean, great discoveries have been made about tilings. A major advance was made by this San Diego housewife. You might have read about her. And only recently they finally finished classifying all the ways that you could tile a plane with pentagons. So yeah, fun stuff. And it's closely related to logic as well. There are these interesting unsolvable problems and there's interesting questions about non-periodic tilings like Penrose tilings that you've probably heard of. And those are kinds of things that not only can high school kids get interested in easily, but they can sometimes make discoveries. I mean, in some of these areas, you don't need to be super advanced in your mathematical background to necessarily make discoveries, and so that's added excitement. Papers get written by high school students, and there was a pretty recent case of a number theory is all being proven by a high school student, and so there's cool stuff that you could do, which might even be new, but it doesn't matter if it is, because you'll have lots of time later, if you don't get run over by a bus, to prove theorems and write programs and do exciting things in math and computer science. And so for the time that you just have fun, learn stuff, maybe apply to college, look for one that does where they do stuff that you're interested in, and there'll be lots of good ones.
Thank you. So as a final question, where do you think that computing is going in the future?
First, I will warn you that everybody's going to have different opinions, and some of which will be way more qualified than mine. But you could see trends. you could see things happen. Lately, we've been watching the rise of machine learning as people have figured out how to make neural nets do a lot of the stuff that we thought would be easier in the beginning, especially stuff related to artificial intelligence. I mean, artificial intelligence, which was practically invented at Dartmouth, um, um, and which was thought about by Alan Turing and all these, and John von Neumann and all these pioneers in computer science. And Isaac Asimov even give these people credit, imagination. We all expected to have robots walking around and almost undistinguishable from humans, and we all expected already in the 20th century to have picture phones and all the rest of this stuff. We're finally getting some of this stuff, and we're finally getting some useful artificial intelligence come about by a somewhat different way than we thought. So I think there's going to be more advances in neural nets. We now know that they can work. We don't exactly know how they work. We're working on that. It's useful to know how they work because if you're going to make decisions using neural nets, you'd like to figure out why they're telling us to do what they're telling us to do. Yeah. So that's one very exciting area. But there's always things going on. And I'm hearing some feedback here for some reason. Okay, I think it's better now. Are you hearing the feedback, Victor?
I'm not hearing any feedback, but it's glitching a bit on my end.
Try turning the volume down slightly at your end.
Yeah. Is it better now?
I think it is better. Yeah. Okay. Right. So so machine learning is a very hot area right now, but security and cryptography is always doing interesting stuff. There are huge advances in graphics. Robotics is loads of fun, and I highly recommend it. In the theory of computing, one of the big new topics is, of course, quantum computing. And there's quite a bit of controversy at this moment about whether quantum computers are going to be useful or not. We know that they exist and they can do something. Recently, quantum supremacy was announced, something that a specially designed problem that it seemed only a quantum computer could do. It turned out that a clever classical computer could also do it. So at the moment, we don't know. I mean, if I had to guess, I would say eventually quantum computers will come into their own. And it may be that as a result of that, a lot of cryptography is going to have to change in order to stay secure. And of course, in the area of applied cryptography and applied theory of computing, cryptocurrency has been a huge thing, which has taken over the world, and a little bit of a lull right now in cryptocurrency, but I don't think that's going away either. I think it was a fantastic idea, and maybe the right version of it that doesn't use all the energy in the world and doesn't have other various problems will eventually take over and give us a universal currency for the world. That would be pretty exciting. So yeah, lots of great stuff going on. I can't think of anything in computer science that's not interesting at the moment.
Yeah, thank you very much for meeting with me and for being willing to do this interview.
You're very welcome, Victor. It's been a pleasure.